Hey guys, this is Gary, and this is the answer key video for Unit 9, Lesson 10. So just remember that we need to be really good at this stuff because we've got our test on Thursday. So a population of rabbits doubles every 60 days. If the population is initial 20 rabbits, I think that has 2 B's, then which of the following is the number of days it takes for the population to reach 320 rabbits? All right, so as always with the word problem, we want to turn it into a formula. So we start off with 20 rabbits. So the population as a function of time is 20 rabbits, and it's going to double every 60 days. So we know we're going to be multiplying 20 by 2. But instead of doing this every day, where t would be the power, we're doing it every 60 days. So if we wait 60 days, we want to double it once. If we wait 120 days, we want to double it twice. So we want to do times 2 twice. If we wait 180 days, then we want to double it for each of the 60 days. So that would be divided by 60. That's 3 times. So we want to double it, and then double it. So it looks like what we want to do is we want to figure out what do we need to do to the number of days to get the number of times it doubles. So at 60 days, it doubles once. With 120 days, it doubles twice. With 180 days, it doubles 3 times. So it looks like what we want to do is, if we wait t days, we have to divide the number of days by 60, so that doubles once. Divide the number of days by 60, so that doubles twice. Divide the number of days by 60, so that doubles 3 times. So this will be t over 60, because it doubles every 60 days. All right, so which of the following is the number of days it takes for the population to reach 320 rabbits? So the population is 320, so we plug that in here. 20 times 2 to the t over 60. We divide by 20 on both sides. We get 160 is equal to, or sorry, 16, excuse me, is equal to 2 to the t over 60. Now we do a log base 2 on both sides to cancel out that base of 2. So this becomes log base 2 of 16 is equal to t over 60. So if we do log base 2 of 16, that's going to look like this on your calculator. So functions miscellaneous log. And then 16 is the main number. And then we divide by log of the subscript, which was 2. So that's 4. So we get 4 is equal to t over 60. We multiply by 60 on both sides. And we get, oops, that doesn't cancel out. We get t is equal to 240. A radioactive substance has an initial mass of 100 grams and a half-life of 4 years. Which expression shows the number of grams remaining after t years? So we start off with 100 grams, and it's going to multiply by half. We'll have half left every 4 years. So what we do is we raise this to t, and because it's every 4 years that it halves, we do t over 4. And that's analogous to this over 60 here, because it was doubling every 60 days. This is halving every 4 days. And to do the reverse of what we did here, maybe an alternate explanation, if we were to plug in 4 here, for t, if we wait 4 years, 4 over 4 would mean it halves once. If we plug in 8 years, 8 over 4, it means that it halves. 8 over 4 is 2, so it'd be twice. And that makes sense because the half-life is 4 years. If we wait 8 years, it will half and then half again. So this definitely is our formula. So that looks like this one right here. Now this one was a pretty tough question that I saw a number of students find challenging the last time I asked it, so I want to make sure that I put it on this homework video. A radioactive substance has a mass of 140 grams at 3 p.m. and 100 grams at 8 p.m. So this is 5 hours later. Using an equation in the form A equals A sub 0 times 1/2 to the t over h, solve for h, the constant representing the number of hours in the half-life h. So they want us to solve for h. In the formula above, A0 is the initial mass, and A is the mass t hours after 3 p.m. Okay, this one's pretty tricky. So thinking about what we are given here, we have to use these values from above. So it looks like it was, I guess, what do we use for the initial mass? Well, I guess we'll use 3 p.m. because that was the first time that they gave us. So we'll say it equals 140, or sorry, A of t equals 140 times 1/2 to the t over h. Now we're really lucky though, because we also get this other point, we could use this value to find out everything else that we don't know. So at 8 p.m. we have 100 grams, so the amount is 100. It's still a half-life, so it's still half. The time that elapses is 5, so it'll be 5 for t, and then h would stay as h, because we're trying to solve for h. So here we go. We divide by 140 on both sides. That gives us 5 over 7. Oh, sorry, I won't write that as a fraction. Let's write that as a decimal. 100 over 40. Over 140, sorry. 0.714285. 0.714285, repeating, equals, and I won't put the repeating because that's confusing potentially, equals 1/2 to the 5 over h. Now, we need to solve for h here, so we need to get rid of this base. To get rid of a base of 1/2, we want to do log base 0.5, because 0.5 is the same thing as 1/2. So you do log base 0.5. That gives us log of 0.714285 divided by log of 0.5 equals 5 over h. So doing the math over here, we get functions log of 0.714285 divided by functions log 0.5, 0.48542, 0.48543 equals 5 over h. Solving for h, we multiply by h on both sides, and we get 0.48543 times h equals this. We divide by 0.48543 on both sides, and we get h is equal to, so let's see if we can copy this. Nope, can't copy it. 5 divided by 0.48542, cool. So 10.3. I really didn't give you guys enough room on this one, I'm sorry. Determine how many hours the mass of the radioactive substance will, determine after how many hours, okay, so we're up to part B. I'm gonna put that here. Determine after how many hours the mass of the radioactive substance will be 40 grams. Round your answer to the nearest tenth of an hour. So once we find the half-life, this is actually always the same. So we can go back to our original formula. A of t is equal to 140, and then it halves every 10.3 hours. Now t is unknown in this case because we don't want to know the t value from before. That was 5 hours. We want to know how long until it's 40 grams. So what we're going to do is we're going to plug in 40 for the amount here, and then we'll solve for t. So if you go through all the algebra, I'm going to skip those steps because I think you guys can see them. T is equal to, you'll do 40 divided by 140. You'll take the log base 0.5 of that whole thing, and then that will cancel out this 1/2. And then finally, you'll multiply by 10.3 on both sides, and that will give you your final answer. So I'm just going to plug that all in on the calculator at once. You could show this step by step, but I'm not. So let's see if we can do it. So this should be log of, wow. Okay, let's get rid of everything. Functions, log 40 divided by 140. That's all inside of the first logarithm. That's all inside of the first logarithm. Then we have to divide that whole thing by log of 0.5, because that was the base. And then we had to multiply that whole thing by 10.3 because that was the half-life, so we get 18.6. So if this was confusing because we took all the algebraic steps at once, just slow it down and make sure you get the same answer, 18.6 hours. All right, let f of x equal this. So we didn't get a chance to talk about this in class, which is a little disappointing, but we can go over it now. So this is a strange problem, and it might look like there's a printing error, actually. It might look like, where's the base? And there is no base there. Sometimes we actually just write logs without bases. And if you have a case like that, all you have to do is just plug in the number exactly like how you might imagine, and then use your calculator to simplify it. So f of 150 means we're plugging in 150 for x, so we plug it in all the x spots, and we find that f of 150 is equal to, and then you just put this whole thing in your calculator. Even though there's no base, it just means you don't have to do any division. It's kind of like ln. So we do 6 functions log, and because there was no base, we just put 150. We don't have to worry about dividing by anything or anything like that. We just put the 150, and then it was plus 2, so we'll have to put the plus 2 on the outside. Oops, plus 2 goes on the outside, so plus 2. And your calculator will just be able to handle that log exactly like how you might imagine, even though it's a little strange looking. If they don't put a base, just type it in exactly how it is. So 15.06. All right, so that's how you do these problems. When they don't give you a base, just put it in on the calculator without the base. This log without a base really means log base 10, but your calculator can handle all of that without you having to worry about it. But if in case you're curious, that's what that really means. A house purchased 5 years ago for $100,000 was just sold for $135,000. Assuming continuous exponential growth, approximate the annual growth rate to the nearest percent. All right, so this one's very similar to one we did in class, so you guys can figure it out. And for problem 6, I'm just going to write the two formulas down because some people just came in and I don't want to keep talking because they've got work to do. So the two formulas for A, it's going to be, I'm just going to be 1 minute, guys, sorry. It's going to be A of t is equal to 5,000, and because it's compounded annually, they get the whole 4.5% at once, so 0.045 to the t power. For option B, because we're getting it quarterly, it's going to be a similar formula. B of t equals, starting at 5,000, times 1 plus 0.045. Quarterly means divide into 4 chunks, and we get it 4 times as frequently, so the power will be 4 to the t power. All right, guys, I hope you found this helpful. Good luck on your test on Thursday, and I'll see you in class.